There are two types of discontinuities, removable and non-removable. This material isn't necessarily going to be on the AP exam, but it's something that's important to realize when you're discussing discontinuities. In regards to removable discontinuities, these are discontinuities which produce basically a hole in the graph. There may or may not be a point on that value of x equals a, but there's definitely a hole in the graph at x equals a. All right, situations like that, and you'll see the picture from one of the other videos. But the situation that you're looking at is something like this, where we have x squared minus 25 over x minus 5. Okay, we know that a discontinuity can occur when the function doesn't exist. So what value of x causes this function not to exist? Exactly, x equals 5, because if x is equal to 5, we are dividing by 0. Okay. However, if we look at the numerator, we could actually factor that numerator. Okay. That numerator, x squared minus 25, can be factored into x plus 5 times x minus 5. We learned that back in algebra. So let's do that. In doing so, we now notice there's an x minus 5 in both the numerator and the denominator. And therefore, we can cancel them, or we can remove the discontinuity. Okay. Now, that doesn't mean that the domain issue still isn't there. Okay. We still have a hole in the graph because ultimately this is our function, not x plus 5. All that what we figured out right here is that x squared minus 25 over x minus 5 behaves like x plus 5. However, we still have that hole in the graph when x is equal to 5. So what we can do is we can redefine the function at x equals 5 in order to get our function to be continuous. And we'll talk about that more in example 20, with example 25 right there. Okay. As far as non-removable discontinuities are concerned, we're not going to be able to remove the issue in the denominator. Let's take this function f and let's reciprocate it. So we now have x minus 5 in the numerator and x squared minus 25 in the denominator. We can still factor the denominator like we did the numerator in the first problem. We have x minus 5 in the numerator. We have x minus 5 times x plus 5 in the denominator. Same factorization. Now, can we remove the x minus 5s? Absolutely. So we have a removable discontinuity right there at x equals 5. We were able to eliminate that issue. That's going to be a hole in the graph. Okay, but this x plus 5, we cannot remove that. We can't cross it out and replace it with a 1 because there's no x plus 5 in the numerator to do that with. And therefore, that x plus 5 still is going to produce a domain issue, particularly when x is equal to negative 5. If x is equal to negative 5, we are dividing by 0. Okay. If x is equal to 5, we are dividing by 0. We can eliminate that one, which means we're going to have a hole in the graph at x equals 5. We cannot eliminate or remove the x plus 5, which means we're now looking at a vertical asymptote. And if you take a look on your graphing calculators at the graph of x minus 5 over x squared minus 25, you will in fact see the vertical asymptote when x is equal to negative 5, and you will see that the graph is undefined. There's a little hole in the graph when x is equal to 5. By hitting the trace button and typing in 5, it'll take you to that spot. You'll see that it says x equals 5 at the bottom of the screen, and then y equals, then there's no value because the function doesn't exist there. That's the idea behind a non-removable discontinuity. There's nothing we can do to get rid of that issue of the 0 in the denominator. So we'll be back in a second to talk more about these examples over my left shoulder.